Poynting's theorem and conservation of energy and momentum recall that the rate of doing work by EM field, equation 7-54, where S vector equals C divided by 4 pi times E vector cross H vector is the Poynting vector. Let's now consider a system involving EM fields and charged particles. Denote the total energy of the particles within the volume V as E sub mech and assume that no particles move out of the volume. Equation 7-55. Then, the energy flow is given by equation 7-56. Thus, equation 7-57. Since we are dealing directly with the particles, not ponderable media, we can use microscopic fields E and B, thus.
Equation 7-58. Consider next conservation of linear momentum, starting with the Lorentz relation. See the next equation, which can be rewritten. See the equation shown. Using the relations, see the next equation. We get.
See the equation shown. The LHS, left-hand side, tells us P vector subfield equals 1 over 4 pi C times E vector cross B vector times d cubed x, and the EM momentum density is G vector equals 1 over 4 pi C times E vector cross B vector. The RHS gives us the EM stress tensor. See the next equation. So, see the equation shown, where the sum from beta 2 of T sub alpha beta n sub beta corresponds to the alpha component of force per unit area across S. Thus, equation 7-59. The above formula can be used to calculate the forces acting on material objects in EM fields by enclosing the object with a boundary surface S and adding up the total electromagnetic force. Note that the stress tensor is not symmetric for anisotropic media.
Example 7.2. Two non-permeable parallel wires, separated by a distance d, form a transmission line with one wire having radius a, the other radius b, connected at their termination n such that current flows down one wire and back up the other. Assume a uniform distribution for the current looping through the wires. What is the self-inductance per unit length? Solution. The current density in the radius a wire is J vector sub a equals I sub z divided by pi a squared times E hat sub z. Using this we have near wire a. See the next equation. Switching to integral form, see the equation shown. Thus, see the next equation. And see the equation shown. For non-permeable medium, the absolute value of B vector equals the absolute value of H vector. Let's get the vector potential. Use of standard formulas then apply. Since B vector equals gradient cross A, we have A of x equals 1 over c integral of the fraction with numerator j of x vector prime, d cubed x prime, and denominator the absolute value of x vector minus x vector prime. Thus, A is parallel to the current. Thus, the only comp of A is A sub z. So,
see the next equation. The only comp of B vector is along E hat sub phi, so see the equation shown. And for region inside or outside the wire we have, see the next equation. And see the equation shown. The vector potential arbitrary up to an additive gradient of a scalar function, continuity of A sub z at surface of wire resolves arbitrariness.
See the next equation. Thus, see the equation shown. The vector potential is thus, see the next equation. Now see the equation shown. And the self-inductance is identified from the terms that result, left as exercise. Example 7.3. Two non-permeable coaxial conductors, separated by a distance b dash, a form a transmission line with the inner conductor being a wire having radius a, while the outer conductor is a cylindrical shell with radius b, connected at their termination n such that current flows down one conductor and back up the other. Assume a uniform distribution for the current looping through the wire or shell. What is the self-inductance per unit length? Solution. Focusing on the inner wire conductor, we know that system energy can be expressed as.
See the next equation, where L sub 1 is the self-inductance desired. Label the wire region 1, the region between the wire and the shell as region 2, the shell as region 3, and the region outside the shell as region 4. We also have system energy in terms of the fields, W equals 1 over 8 pi integral of h vector b vector d cubed x equals the fraction with numerator mu to the negative 1 and denominator 8 pi integral of b squared d cubed x, where d equals epsilon e and h equals 1 over mu b. Region I. See the equation shown. See the next equation. See the equation shown. Energy per unit length in 1.
See the next equation. Region 2. See the equation shown. See the next equation. W sub 2 equals the fraction with numerator mu to the negative 1 and denominator 8 pi the integral from 0 to 2 pi of the integral from 0 to b of 2I mu over rho c squared rho d phi. The absolute value of b equals 2I mu sub 0 over rho c. See the equation shown. Region 3.
See the next equation. See the equation shown. W sub 3 equals the fraction with numerator mu to the negative 1 and denominator 8 pi the integral from 0 to 2 pi of the integral from b to c of 2 mu I over c squared. The absolute value of b equals 2 mu over c rho I times 1 minus the fraction with numerator rho squared minus b squared, and denominator c squared minus b squared. See the next equation. Region 4. See the equation shown. Thus, assuming mu equals mu sub 0.
See the next equation. Example 7.4. A betatron has a toroidal region with constant E field and the axial B field is B sub z of r t equals CTR to the nth power for t is greater than or equal to 0. Find the induced E field. Find the velocity v of a particle at time t where that particle is assumed to stay at radius a. What is the magnetic force on the charge? For what values of n will there be a path of constant radius as assumed? Solution. Recall. See the equation shown. Take the line integral to be a circle of radius a in the betatron, centered on the z-axis. See the next equation. So see the equation shown. And E is tangential to the circle circulating clockwise when viewed from above. Since F vector equals QE vector and F vector equals MA, we have.
See the next equation. Thus see the equation shown. And is directed tangentially to the circle at radius A. Since see the next equation. The magnetic force on a charged particle is. See the equation shown. And if V uptack B like here we have.
See the next equation. Centrifugal force equals mb squared over a. So for this to balance the magnetic force, see the equation shown. Which requires n plus 2 equals 1, thus n equals negative 1. Example 7.5. Consider a parallel plate transmission line as described in a previous example with plate separation, a width w, and ignoring internal inductance. 1. What is the characteristic impedance? Consider a computer circuit with such lines having W equals 5 mu m and A equals 1 mu m. The relative permittivity is 2.5 and the relative permeability is 1.0, typical. 2. What is the characteristic impedance and wave velocity? 3. Have the dielectric thickness, what happens? Solution. I along A unit length we have C equals epsilon W over A, F is the units farads, and L equals mu, A, over WH over M, with H being the unit of henries. Together with Z equals LV and V equals LC, raised to the negative 1/2 power, we get.
See the next equation. Again, showing units explicitly, here ohms omega. Thus, see the equation shown. 2. Z sub 0 equals 1/5 the square root of 1 over 2.5 times 377 OH of ms equals 47.8 omega and V equals the fraction with numerator 1 and denominator the square root of epsilon mu equals 0.6325 C equals 1.9 times 10 to the 8th power m over s. 3. If A equals 0.5 mu m we see that the impedance is simply halved, while the wave velocity is unchanged.